So today is going to be another day where we're not really going to do any calculations. I just want to talk about a lot of important ideas that we will be needing. So let's just jump back into it. Last time we learned about an idea called concavity, where there were two flavors. You can have concave up, you can have concave down. And these are all about shape, right? So concave up just means you're shaped like a smiley face. So you have this, like that. Right? So concave up like a cup. Right? And the defining characteristic of that, computationally speaking, was if you calculate the second derivative at any point, right? So a random point on a function that's exhibiting this behavior, you'll notice that the second derivative at that point will be positive, will be greater than 0. Right? So once your second derivative is greater than 0, you get this kind of bending that's kind of like a cup or a smiley face. Concave down is like this, like that, or like that. Okay? So concave down like a frown. Okay? So you shape like a frowny face, and if you were to pick a random point, when a function is exhibiting this behavior, you compute the second derivative at that point. You get the second derivative is negative; it will be less than 0. So now I want to talk about some more nuances that concavity can give us. The idea of an inflection. So a point of inflection is a point where we switch concavity. So you could have been concave down, then there came a point where you switch to concave up. Right? So that point would be an inflection point. Right? Or you could have been concave up, there came a point where you switch to concave down. That's called an inflection point. So these are two increasing examples. You could have decreasing examples. So you could be going down, and then you switch like that. Down like this, and you switch like that. So there comes a point where concavity is changed. So here's the point. Notice that on the left side of it, we are concave down, while on the right side of it, we are concave up. This location where you actually make that switch is called a point of inflection. So these points indicated here, these points here are points of inflection because we changed concavity at those points. So, and either direction is going to be, it's going to be fine. So also, if you here you switch from concave up to concave down, or concave down to concave up, these are called points of inflections where that happens. And what I want you to do, this is of course applied math, consider the meaning of these when an interpretation is given to our function. So, I know not everyone here is a math person. Math people, we care about the math, we care about the function. You're such a beautiful function, I want to know all about you. Not everyone is like that, understood. But functions are useful because of what they can tell us based on what the function actually represents. So the function might not be important to you, these particular shapes might not be important to you, but what they're representing and the interpretations of that is what's going to be important. What I want to convince you of at this point is these things have several important interpretations. Okay? So last time we spoke about the idea of increasing and decreasing. So increasing means as you're moving from left to right, the graph is going up, right? So both of these situations here represent an increasing situation. Decreasing means as you're moving from left to right, so as you go from left to right, the graph is going down. Same thing here, the graph is going down as you go from left to right. These represent a decreasing situation, right? So increasing, you're going up. Decreasing, you're going down. Of course, how you would interpret that is something's getting bigger or smaller, whatever you're actually measuring. What interpretation can you put on top of that that somehow is useful? These two will actually illustrate that. Both of these guys are increasing, but notice that they're increasing very differently. In fact, they're increasing with an inflection. What this would sort of mean, this kind of shape here, means you're increasing, but you're increasing slower and slower. The rate of increase is slowing down. Whereas here, you're increasing, but you're increasing faster and faster. You're getting steeper and steeper. So your rate of increase is going up. Now, whether that's good or bad is entirely going to depend on the interpretation of the function. If I'm plotting this function and it is the profit I am making from selling a product or a service, these two situations are good, these two are bad. If the function is representing the amount of malignant cancer cells in my lungs, these situations are bad, these situations are good. Well, if you're in any of these situations, it's bad, but you get what I'm saying. If I had to be in one, I'd rather be over here than over here, right? So good and bad can depends on the interpretation of the function. So now, let's go back to the profit idea. Okay, these two saying profit is increasing, but what is the story behind it here, right? Is this situation better or that situation better if it comes to profit? Both are good, but which would you rather be in, right? They are actually very distinct. So, in this situation, what's happening? Business is good, it's all right, yeah, we're doing well, we're making a profit every day, but profits are slowing down. Something happened. Whoa, now business is great, things are really good. Wow, we're getting better every week, right? So here, this kind of would represent a situation of going from good to great, right? The system, at this point, things just keep getting better and better. So if you were interested in getting as much profit as possible, one thing you might want to do is figure out where such an inflection point would occur, and whatever happened at that point, do more of that. Okay, so business was good, but we started a new ad campaign, and then whoa, hey, let's have more ad campaigns like that. Or, business was good, but then we hired John, and he's awesome, and he put this department in shape. Let's hire more people like John, right? So this point would represent some event happening that changed how you were increasing. And again, it can be good or bad. Here, you're increasing. Profits are good. And over here, once you pass this point, profits are still good, but they're slowing down. What happened? Maybe a competitor opened a store around the block or something, right? So we're still making money, people still love us, but they are stealing some of our customers. How would we do that? Right? And you can kind of see, well, I can also kind of see if we continue on this path, it's probably not going to end up well. So it gives you some sort of predictive power. Not only do you see when things are going up or down, how are they going up? How are they going down? What does this mean? What could this mean in the future? Whenever you're asking questions on that level, that's a whole other level. The second derivative is what's going to take you to that level, right? The first derivative can just tell you, oh, it's going up or down. The second derivative is going to tell you, here's how it's going up, here's how it's going down. Here's what you could potentially look forward to in the future. The second derivative is going to add another dimension on the interpretation of your function. And a lot of times that can matter. So another example would be, recently, if you look at like climate change, and people are like, oh, climate change is a hoax, the global temperatures have always been rising. Yeah, they've been rising, but then the Industrial Revolution happened, and now that's happening. And you know what? There are consequences to that, right? So sometimes how things are increasing actually matters. It's not just a matter of we're getting more of this stuff. How are we getting more of it? What would that mean? What are the consequences of this? Your second derivative is what's going to tell you about that. Right? So seeing these behaviors is not just this thing that you'll learn in math class. If you see these on a picture in real life, in something that you actually care about, you need to know how to interpret. Is this good or bad? What are we looking at? And even if it's good, is it good going on great, or is it good like it's about to get bad? Like all those kinds of questions, second derivative concavity inflections gets you to that level of analysis. Now, to further help you analyze things, there are going to be two tests that I want you to know that we're going to be able to apply at some later point. So, one, I want you to know a test called the first derivative test. As its name suggests, this one uses the first derivative. The second test I want you to know is called the concavity test. Since we know that second derivative defines concavity, this one is going to involve the second derivative. There's another test called the second derivative test, which is different from these, and that's kind of important to know for traditional reasons, really. Like every textbook is going to mention it. I'll probably mention it in passing a little bit later, but it's not going to be important for us because all the information that you can get from the second derivative test, you will be able to get that information from the first derivative test. And usually, the kinds of questions I would ask you, you're going to have to use the first derivative test anyway, so it kind of makes the second derivative test superfluous. So you won't actually ever use it, or you won't ever need to use it. Although, I'll probably mention it at some point. But these two tests, you're definitely going to use these at some point. So we should know what they are. So, let's talk about the first derivative test. How do we do it, and what does it help us discover? What is it a test for? So, given f of x, this helps us find where it is increasing or decreasing, and if there are maximums or minimums. All right, so maximums and minimums, very important thing to locate. Now, for certain kinds of functions, we actually know how to do this. So if you're looking at a quadratic, you know how to find a maximum or minimum. Just find the vertex. Turns out that in general, it's not that easy. If I give you a random function, chances are you're not going to know a nice formula like a vertex formula that's going to locate the maximum or minimum for you. You can, however, use the first derivative to locate a maximum or minimum. That's one of the most important reasons why you would need a first derivative. The second one is approximation, but maximums, this means you have a situation like you're at the top of a hill. And minimum means like you're at the depth of a valley, right? And of course, knowing when something is as big as it can possibly be, or as big as it can possibly attain, or as small as it can possibly attain, these are important things. The first derivative test is going to help us with that. So, I have a function. I want to know, where is it increasing? Where is it decreasing? Does it have maximums and minimums? I would use the first derivative test. And the first step is that you're going to find f prime, the first derivative, and the so-called critical points. What is a critical point? This is a point where the first derivative is 0, or the first derivative is undefined. And at some later point, I'll tell you why those two are actually important. You need to locate all points where your first derivative is going to be 0 or undefined. These are critical points. Now, of course, you're going to calculate the first derivative. You're going to set it equal to 0, solve for all the x values. You're going to see is there any x values that makes this undefined? You're going to figure out what those x values are as well. The next thing you're going to do after doing that, you're going to plot the critical number points on a number line. Now there are other ways to actually do this, but I think plotting it on a number line, having that visual cue is important to just keep things organized, making sure you're not missing anything. Test the intervals. Now what do I mean by test the intervals? You're going to plug in random numbers. So you're going to have a number line. I usually would label this f prime because there are a couple number lines that we're going to use and I don't want you to mix them up. So there's a number line that I'm having in mind, the first derivative, label that f prime. Now let's say I have a critical point. That's here. This is x. This is my critical point. So this is an x value where the derivative is either going to be 0 or undefined. This is going to be plotted on the number line. What you're going to do is you're going to pick a random number on either side of x. Pick an x0 and pick an x1. And what you're going to actually do is you're actually going to calculate the derivative at those points. So that is going to be the second phase. Now the third phase is the most fun part. You can now make certain conclusions. So you're going to be able to make conclusions based on the following. So a couple important situations are these two. And pretty much the only other important thing is to know when one of these two does not happen. So here's our x, the critical point. Here's something that you can occur. Let's say you pick a value over here and your first derivative at that value is positive. And you pick a value over here, your first derivative at that value is negative. Now notice what that would actually mean. When your first derivative is positive, that means you're increasing. It means your function is going up as you go from left to right. If your first derivative is negative, that means decreasing. This means your function is going down as you go from left to right. So what do you think that would make this point? Yeah?
Maximum.
It's a maximum. Provided there's one caveat though, because there might be a gap or a hole or something there. So the one caveat is if your f of x is continuous here. Then this situation is a maximum. Right? So this is a point on the graph, it's actually filled in, we can get to that location. And I'm increasing on the left, I hit that point, and then I immediately start to decrease. That behavior happens when you hit a maximum. Another similar situation. What if you got the first derivative on this side, you tested that was negative? Well, that means it's decreasing. And then on the other side, you tested a function, f prime, and it's increasing. So if your derivative is negative on the left and it's positive on the right, and assuming that this is actually a point on my function, f of x is continuous here, then this situation means a minimum occurred. Okay. Now, otherwise, no maximum. But we can still determine increasing or decreasing. Right? Because again, remember, increasing just means you're moving up as you go from left to right. So I can tell you where it's increasing, I can tell you where it's decreasing. But a maximum occurs when you're in this situation, a minimum occurs when you're in this situation. Otherwise, there is no max or min. But when the derivative is positive or negative, you can talk about increasing and decreasing. Yeah.
When you try to find if the function is continuous, like, are you trying to find it based off of its like original function or the derivative of it?
The original function.
The original.
Yeah. So it's f of x is continuous, which means you're going to check, is the limit as I approach the point equal to the value of the function? Or is it one of those 6 nice functions, a polynomial or a rational or radical or something that's really nice? So yeah, I'm talking about the original function you're going to test it. The only time you actually plug anything into the first derivative is when you're coming up with this chart right here. And we'll talk a little bit more about that actually towards the end. But that's the first derivative test. It's a 3-step process. By the 3rd step, you'll be able to make certain conclusions. You'll be able to make conclusions about increasing, decreasing, maximums, or minimums. Right? So one of the most important uses of the derivative is to actually locate maximums and minimums and increasing and decreasing. Because actually doing that in general is not easy. Not all functions have a nice formula that can give you a vertex or whatever. That's the first derivative test. Let's talk about the concavity test. It's actually going to be very, very similar, except instead of the first derivative, you're going to use the second derivative, and the interpretations, therefore, will change. So, the second thing you want to know, the concavity test. Why would we need this? Given f of x, we want to find concavity, right? Either up or down. Right? So up, if you're increasing concave up, notice you're increasing faster and faster. So something like that might be interested, you might be interested in knowing. So this tells you the speed at which your speed is changing. So concavity might be important for that. And inflections. So when that is your goal, I want to know what is the concavity of the situation here, and are there any inflection points? You are going to do the concavity test. Now in step 1, you're going to find the second derivative and the critical points. So, of course, once you find the second derivative, figure out where is it 0 and where is it undefined. Okay, you're going to find all that. Then, again, plot on the number line. Test the intervals that it creates in f double prime. So you're going to draw your number line. You're going to label that f double prime because you don't want to mix it up with the number line from the previous step. Right? You're going to plot all the points you found in step 1, and then again you're going to pick a random number over here, random number over there, and you're going to find the second derivative at these points. So you pick a point x0, doesn't matter what it is, as long as it's not overlapping with other critical points, it's in between all the critical points. And you're going to find the second derivative at these points. Now, once you actually make those computations, you are going to make certain conclusions based on that. So the third step would be to conclude based on the following. Again, here there are 2 situations that you would want to care about. So here are your x values. At these points, your second derivative is 0 or undefined. Now let's say you plug in a random number over here, and your second derivative is positive. What that means, concave up. So I draw a smiley face to indicate that I don't care about increasing or decreasing. I don't care if it's going up or down. That's not the point. Is it shaped like a smiley face? Is it up like a cup? Right? Then over here, I'll do a second derivative. And let's say it's like that. Now it's down like a frown. So So notice this point here is concave up, this point here is concave down. Now, if the original function f of x is continuous here, this situation is a point of inflection. Now, you could be increasing or decreasing, it's not going to matter, but the point is you either have a behavior like this, or you have a behavior like that happening at this location. The other situation is they switch sign in the other way. So you can have your second derivative is negative over here, so you should have a frowny face. Or you can have your second derivative is positive, so over here it's shaped like a smiley face. So you were concave down to begin with, now you're concave up. And assuming your f of x is continuous at this point. So there's no break, there's no gap, there's no hole, there's no like vertical asymptote. This situation is also a point of inflection. So in this particular situation, it means that you either have this behavior or you have this behavior. Otherwise, no inflection. But we can determine concavity. So remember, an inflection point is just where you switch concavity. So I was concave up, then I switched to concave down. Or I was concave down, then I switched to concave up. That behavior indicates an inflection occurred. Right? Now, if that doesn't happen, or something similar to this happens, but I'm actually not continuous at that point, then no inflection happened, but you can still talk about concavity. I know I'm concave up here, I'm concave down there, that sort of thing. And that's the concavity test. I got some time to finish copying that down. Now, I just want to summarize the main ideas that we were talking about last class and today's class, functions and their meaning. To make sure we all know what each function can do for us. So let's say we're looking at a function. When you look at a function, I want you to know, what does it tell you? So you're going to know that. Then you want to know, how does it tell you? So you're looking at a function, what kind of information can I get from this function? And how would I be able to interpret that that's the information that's being conveyed to me? Okay, so those are the two things. So the first one is the original function, f of x. So I give you a random function. What information can that give you and how can it give you? Well, if I give you y equals f of x, what am I actually telling you? Well, I'm telling you, if you know a certain x value, use this formula to figure out the y value. In other words, I'm telling you things like location, point on graph, current status, that kind of thing. So if this is measuring my profit, you would use f of x to answer questions like, how much profit did we make this week? Right? What is our profit looking like now? Right? Someone asks those kinds of questions, you would look at the original profit function. Right? Now, how is it going to tell you? Well, we all kind of know that idea. You plug in x, compute the y. And x comma y gives location. Status. So that's the original function. And that we've known for a while. We've been playing around with functions for a long time at this point. Now, perhaps new to some of you, a new function comes on the scene that we call the derivative. Now, what is the information that that function tells us? Well, this one tells us about when something is increasing, when something is decreasing, and if and where are there maximums and minimums. So, someone asks the question, are our profits increasing? Is business good? The first derivative answers that question. What is the profit that we made this week? The original function answers that question. Right? So if you want to figure out increasing, decreasing, maximums, or minimums, you look at the first derivative. That's what this function tells you about. How does it tell you? The first derivative test is how it tells you. Then we looked at another function. The second derivative. So sometimes after you take a derivative, you can take one again. This causes you to calculate the second derivative. What information can you get from that function? Well, concavity. Whether something's concave up or down. And remember, this is shape. It doesn't mean increasing or decreasing. It has nothing to do with up or down. It just means how are you shaped while you're moving up or down, right? Are you shaped like a smiley face or a frowning face? Now, unfortunately, they use the words up and down in the name, but it has nothing to do with moving up or down, right? Concave up like a cup, down like a frown. It's about the shape of the graph. Another thing it can give you information on is inflections. And like I said, these things can give you a lot of interpretive power as to what your function is doing, or the thing it's measuring, how is it behaving. How does it tell you? The concavity test is how it's going to tell you. Do the concavity test and it will tell you exactly what the concavity is and if there are any inflections. So that's kind of the summary. You need to know, if you're in a situation where you're looking for a specific thing, you need to know which one of these functions is going to give you the answer that you want, and how would you actually go about getting that answer. So, if you have a function and you wanted to discover the maximum point, where is this a maximum? When are we having the maximum profit? What you would do is you would first go to the first order. You would figure out, use the first order test to figure out when a max would happen, to actually figure out the location of that maximum, because all this is going to tell you is the x value. You go to the original function to find the y value, and then you can say, okay, at this point, there's a maximum. Right? So depending on what you're looking for, you need to know to use the right function. So if you're looking for concavity, is there an inflection point? You're not supposed to be looking here. You're not supposed to be looking there. You're supposed to be looking here. Right? So each different function has a very specific use. You need to know the uses of these functions, and also how to actually get that information. So these two we spoke about today, and that one you've known for years at this point. Now, this all assumes one very important thing, that finding these guys are possible in the first place. Now, remember what the derivative is. It's a limit. The limit is h over 0 of the difference quotient, right? which means it's possible that f prime does not exist. So when would this be an issue, right? So you know the derivative and the second derivative are very powerful in helping you identify these qualities on your graph or on something that you're measuring. But how do you even know that it's possible for you to find them in the first place? Well, that's what we're going to talk about now, the existence of the derivative. When would a derivative not exist, more specifically? The derivative will not exist in 3 situations. You can pretty much do 3 general situations where you're not going to be able to find a derivative. So the first situation, when is it not possible to compute a derivative? At what point will the derivative not behave? It's not something that can be calculated. At sharp corners and cusps. A cusp is also sharp corners, just a little faster. So if you look like this, or like this, so that would be called a cusp, or like that. Right? So at all these points here, you actually can't find a derivative. So at sharp corners, you actually can't find a derivative. Canonical example, f of x equals absolute value of x has no derivative at x equals 0. So this is a function that we all know, it's the v, bless you, and it turns out that at the corner of that v, you actually can't find a derivative. How do we know? Well, we know what f prime is. This is the limit as h approaches 0 of f of x plus h minus f of x over h. So what would the f prime of 0 be, the derivative at 0? Well, this would be the limit as h approaches 0 of the absolute value of 0 plus h minus the absolute value of 0 all over h. This is just the limit as h approaches 0 of absolute value of h over h. Now it turns out we've actually looked at that limit before. It does not exist was the answer. Of course, when we looked at it in class, we had x. The limit as x approaches 0 of absolute value of x over x. We actually looked at that before. The absolute value means, if we're coming from the right of 0, it returns h, which makes this simplified a positive 1. If we're coming from the left of 0, this simplifies as minus h, which means it simplifies to minus 1. So this graph actually looked like that. And so at this point, the left and right don't match up. It does not exist. Turns out you can't find a derivative at that point. It doesn't exist. And another way you can see that this actually makes sense is that remember what a derivative was trying to do. It was trying to create a tangent line. What is the tangent line? It's a line that touches the curve at one point, that when you zoom in, the curve starts to look like that line. Now, how much do you have to zoom in to get a sharp point to look like a line? It's never going to look like a line. I can draw tons of lines through this point, but none of them will have the property that, you know what, it's starting to look sharp now that I'm zooming in. It's not going to happen, right? You will have an undefined tangent line here. You can draw all the lines you want, none of them are going to fit the bill for what a tangent line has to do, right? So it's undefined. There is no line that you can zoom in and, okay, now it's starting to look like that curve. Not going to happen, right? So sharp corners, bad for a derivative. Can't compute a derivative at a sharp corner. So don't even try. To be fair though, if there's a sharp corner, that would be considered a critical point as well, because that would be a situation where the derivative is not defined. It's still something that you have to look at, but you should just know, don't waste your time trying to find the derivative. Second situation. This one is actually a little more obvious. If f of x is not continuous. So if you have a function and there's a hole, or like there's an asymptote, vertical asymptote. So let's say this is at A, and this is at A. Then f prime of A does not exist. It's undefined here, right? It's a hole. Or if you zoom in, it's just going to be a gap. It's not going to look like a line. It's not going to level out. There's no line you can draw to this point because the point isn't there to draw the line to. So tangent lines will not exist where your function does not exist itself. You can't draw a tangent line to something that isn't there. So that should be a little more obvious. So the sharp corners you have to actually think about it a little, but it's not going to work. And of course, if your function itself is not working, you can't draw a tangent line to that function. So sharp corners, bad. And where there are holes, gaps, breaks, disruptions, also bad. The third situation, now this one is somewhat strange. We won't encounter it a lot, but it is a thing out there. So I'm going to tell you about it. And these are at points where the function would have a vertical tangent line. Now, yes, functions have to pass the vertical line test, otherwise they're not functions. But some functions have this property where they go vertical for like a split second, literally like for 1 point, and then they come out of it, and at that point you won't be able to find a tangent line. So it's like it's doing this like a very, very steep descent, right? So it's almost descending vertically, and then suddenly before it goes vertical, it slips out of it. Now it turns out that if you were to draw a tangent line here, the best line to draw would actually be a vertical one going through that point. Like if you zoom in on this to try to make it look like a line, a vertical line would be the best one to draw. So, vertical tangent. But, of course you know, vertical lines don't have slopes. So, your f prime undefined at this point. So some functions can have that little weird behavior, like they almost go vertical and then slip out. At that point, where they're like literally vertical for that 1 point, you're not going to be able to find the tangent line. Or you, more specifically, you won't be able to find the slope of a tangent line there, which is what the derivative is. It's the slope of the tangent line. So in the first two situations, you can't find a tangent line in general. In this situation, you can find a tangent line, but it has no slope. And that's all I wanted to talk about today. So these are some important ideas that we will be using in the future. So know how to calculate derivatives, and we're going to look at nicer ways to calculate derivatives. Know what each derivative tells you. What does the first derivative tell you? What does the second derivative tell you? And then know when would a derivative not work? When can I not take a derivative? Those are important ideas to know that we will be continuing with in the future. And I will see you guys on Friday.